Okay, welcome everybody. So I think we can get started on today's lab. So today is the first lab of the semester. Last week we just had sort of an orientation, giving you an idea of what the online labs will look like. And so today will be our first online lab. And the topic of today's lab will have to do with uncertainty analysis in the context of a swinging pendulum. So specifically, we'll measure the period of a swinging pendulum. So if you were to imagine a pendulum swinging back and forth, the period of that swing would be the time it takes for it to go back and then return to its initial position. So what we'll emphasize in the lab is that there's two parts of the experiment. There's a theoretical equation where you could calculate what you would expect the period to be, but we'll also measure the data associated with the period. We'll actually use a digital stopwatch that's available in the online simulator we'll use. You'll be able to measure that period yourself experimentally, and we'll work through the uncertainty analysis that's associated with being able to understand your experimental results that have some uncertainty and understand how they fit in with the theoretical calculation, which will also have some uncertainty. So I've just recently posted the document for Lab 1 today. So it's unfortunately I wasn't able to post it soon enough so that you could really get a head start on it. But we'll definitely use all the time we need to today to make sure everyone is clear on the assignment. It's posted on Canvas. I just finished working on it this morning, so I posted it as soon as it was ready, and so we'll work through that today. But of course, going forward, yeah, I'll always try to post them as soon as possible so you can take a look at it, and and then come to class at least a little bit more prepared. So if you haven't already, definitely go to the Canvas website, go to the Files tab, and there should be a Word document there, Lab 1. And so you can download that Word document. And so it's a Word document, so you'll be able to edit it. And that is the document that you'll edit and save your work in, and then eventually upload it to Canvas when you're ready to submit the assignment. And you can, of course, submit it multiple times. If you submit it once early, and then you think, oh, actually I want to change this or add something else, you can definitely submit it at any point before the due date, and I'll look at your most recent submission. So that way there could be even with the potential for feedback there and multiple drafts of your lab submissions. So if you've gone to the Canvas website and downloaded it, you'll kind of get an idea of what it is. It's just a list of, well, it starts off, it's a list of instructions. It also gives you gives you the website, which we'll be using today. And of course, it's sort of styled in sort of a worksheet format. So you're able to just follow the numerical instructions through and complete tables and do the data analysis at each step. So it should be pretty straightforward how you can approach the labs just by following the instructions. My intention, of course, is to make it all clear and not make you have to make too many assumptions on your own. So it should be clear the work that I'll set out for you. And so for those of you who are in my class, this lab is probably going to be a little bit more relevant to the people who are in my class, in my lecture section. But if you're not in my lecture section, that's fine. That's no problem at all. I'll still go through the lab in entirety. So even if you're not in my lecture, you're still going to know everything you'll need to know to complete the lab. So it should be, so it might be, the pace as I go through the lab might be a little bit slower, for the people who are enrolled in my lecture, because, those ideas are very familiar. They should be more familiar to you. But I want to go through, each step carefully so everyone understands what the lab is about, even if you're just taking the lecture portion with a different professor. All right, so the lab document is on Canvas. So if you pull that up, if you haven't already, you don't have to pull it up. You can just watch me. Of course, I am I am recording, and so I will post this in case you want to watch it again. But of course, I always recommend always attending the live lectures, because then you can talk with the class and myself in the chat or via the webcam. All right, so if you download the Word document off of Canvas, this is what you should see. So it just starts off with some overarching instructions. If you have numbers in your data tables, be sure to include units. If there's a calculation, you'll show the steps. So not just do it in your calculator and enter the number in the table. It's good practice to just show those steps digitally in the Word document, in the Word document itself, and I'll show you what I mean by that. Just basically having the equation, and then plugging in the numbers and showing the result. If you want to work together on labs, you can definitely communicate with each other, but you can't have any copy pasting of any sort. No, you don't divvy up the work. So one person does a derivation, one person puts the data in, puts the information in tables. I'd like to, I want everyone to replicate the work themselves, even if you are communicating with someone else, so that you're all doing the same thing. Just make sure each person completes each step themselves independently. All right, so the link for today's website can be followed by clicking on that hyperlink. You'll choose the third selection here. They're all the same simulator, just with different capabilities that are turned on. So you'll use the lab selection, and you'll see this simulator, which is a pendulum, and you can move the pendulum to an initial position, release it, and then you can see the pendulum swinging back and forth. And of course, it's an ideal pendulum, so you wouldn't have the same amount of experimental uncertainties that you would have in a real experiment, but we'll still be able to simulate it to a certain extent. So it's just a pendulum type motion, so a back and forth type motion, and you'll measure the period it takes to go back and forth. So one period would be starting from one side, allow it to swing, and then allow it to return, and then that will be one entire period. And the equation that dictates how a pendulum will swing back and forth in the context of its period is this equation here. So its period is symbolized with capital T. The length of the pendulum and is capital L, and gravitational acceleration is g. And of course, 2 pi is the familiar 2 pi that you know. And I've prompted with these conditions, so a certain mass on the end of the pendulum, a certain length of the pendulum, and of course nominal gravitational acceleration, 9.81 meters per second squared. And you can change that, up here on the right, where we can vary the length. You can see it can change at real time. And if you wanted to see how changing a variable changes the results of the experiment, that one equation that I just showed for the period, the reason why we have equations is that one single equation describes every single possibility, every single length, and every single mass is all encapsulated by that one equation. That one equation completely describes any possible length, any possible acceleration due to gravity, any of that you could imagine. That one equation is capable of describing implicitly. So you can definitely play with these parameters, so you get an idea of the physics of a pendulum and how changing a variable would change the resulting experiment. but I do prompt you with numbers. I'll demonstrate with different numbers, so that way, you'll still have reason to repeat what I do, just with different numbers. So I'll just use, a length of 0.7 meters, a mass of 1 kilogram, and gravity 9.81, the nominal gravity. To measure the time, there is, if you select this stopwatch on the lower left corner, you can stop and start it whenever you like. And so we'll definitely be using that to measure to have an experimental measurement of the period. So our variables here, I'll use slightly different values rather than 0.8 length and 1.5 kilograms because so there's different numbers involved. So for the length, the length is given as as 70 centimeters, or 0.8 or 0.7 meters. So yeah, we'll be using .7 rather than 0.8. So I hope that's not a point of confusion. But the uncertainty in the length, if we think about the uncertainty in the length, so we have just the length of the length of the pendulum string is the distance from the pivot point at the top to the center of mass of the pendulum. So there is a middle line in the mass of the pendulum indicating its center of mass. So if we did, the length is given to us as 0.7 meters, but if we, there's also a ruler here. If we wanted to measure the length, experimentally, or at least simulate it experimentally, if we measure from the fulcrum to the center of mass of the pendulum, we see that it is 70 centimeters, and the limitation of the measuring instrument here, the ruler, is in increments of millimeters, or not in millimeters, or in in centimeters. So 70 centimeters, 0.7 meters, and the uncertainty is 1 centimeter. So you see these little notch marks on the ruler. It's perhaps possible that we could estimate it a little bit more accurately, but because the notch marks on the ruler only are in increments of 1 centimeter, our limitation of our uncertainty in the measurement of the length would be 1 centimeter. So the uncertainty of our measured length is 1 centimeter, which we should note is 0.01 meters. And the reason why we have that uncertainty is because the notches on the ruler are no more accurate than 1 centimeter. And so we can't report a number that's more accurate than what our measuring instrument is limited to. And it could definitely be useful to highlight your answers. I'll highlight my answers here just to emphasize, what you'll have to add, to your own lab document report. So the uncertainty in gravitational acceleration g, well, g is given as 9.81 meters per second squared, which is, taken as a constant, although there is some variability in gravitational acceleration just due to location. Where you are on the Earth, there's variations in acceleration. The constant itself can be known to a large number of decimal places, but within the simulator itself, it can be only accurate to the tenths place. So the uncertainty of gravitational acceleration, I would say, is 0.01. You'll note in the in the simulator, we're not measuring g in the same way that we're measuring length. So we determine the uncertainty in our length by considering the fact that the ruler itself has a limitation of 1 centimeter in its markings. But when we're told the gravity, there's no instrument associated with understanding its uncertainty. We're just given its value as a constant. And so its value as a constant is 9.81, which is, we're assuming that gravity is constant up until the 100th place. So even though, the gravitational constant could be approximated with even more digits, we're making an assumption that gravity is constant, and we only know it to a certain precision. Our level of precision is the 100th place, and so the 100th place will assume that we know gravity is 9.81. It could be 9.82. It could be 9.80. But basically, it's plus or minus 0.01. So I'll add the plus and minuses here to emphasize that fact. And so how we chose that uncertainty was not a limitation in any measuring device, but really we just considered the decimal places. We know gravity is given as a constant, accurate to the 100th place, and so we're assuming that gravity is a constant known to a certain level of precision. So our reasoning there is we're assuming gravity is known to a certain level of precision. That level of precision is the 100th place in the decimal. Yeah, because it is an assumption, because there could be additional uncertainties depending on, where you are. If you're on a mountain, or if you're by a lake, those local characteristics, do have the potential to change what the gravitational constant is. So we are just assuming sort of a nominal uncertainty there, just by the fact of the information of what we're given. All right, so those are our uncertainties in sort of the measurements, that will come in when we make the calculation, because we can theoretically predict the period now with the length and the gravitational constant g. And so if we know the uncertainty in those values, there'll be a corresponding uncertainty in the period t if we were to use the equation. But what if we were to measure t experimentally? And that's what you'll do yourself. So a reminder, I'm using a different length than what you are prompted to do in the lab. You'll be doing a length of 80 centimeters, or 0.8 meters rather than 0.7. So to measure the period, I've prompted you to start the pendulum at 40 degrees, just release it and allow it to swing back and forth. So to measure the period, you'll use the stopwatch. So I have the stopwatch here, and I'll start the stopwatch when it reaches its highest point on the right. Then I'll time it while it swings to the left, and then it'll swing back. And then so once it returns to its initial position, it's made one complete swing back and forth, and so that'll be one complete period. And so if I measure the period once, I'll start it at its highest point on the right. So I'll start that now and stop. All right, so I just measured the period, the time it takes for it to make one swing back and forth. And so that experimental data point is 1.66. So I'd record that in the table. 1.66. Don't forget the units. The units are units of seconds. And you'll repeat that 4 more times. So a total of 5 different times. And so that's where the experimental variation can occur. So I'll just reset the stopwatch. Again, do the same thing. Just measure the period, starting when it's at its highest most point, and stopping it when it returns to that point. So start, stop. All right, just like that. So this time I got 1.77. So I would record 1.77. I would repeat that 5 more times. All right, so I got 1.66 again. So I'll copy and paste that in. Just I'll collect all the data so I can show you. And then so my final data point, I got 1.69 for the period. So we've collected our 5 data points. With that set of data, we'll want to calculate an average and a standard deviation. And so I use an online calculator for that. Specifically, I just Googled standard deviation calculator, went to the first link, and you can plug in your data separated by commas, and you will use population standard deviation. Sometimes you'll see whenever you calculate standard deviation, you have the choice to do population or sample. The only difference is that if you have a data set and you're calculating the standard deviation, if you use all of your data, it's population because it's the entire population. But if you just use a subset of all of your data, then you would use sample. So they're very similar calculations, subtly different, but we'll pretty much always use population standard deviation. As long as you're using all of the data that you have available, that will be the entire population. So you'll always use population. All right, so we have so if I just enter my data separated by commas, so 1.66, 1.77, 1.66, 1.62, 1.69. All right, this gives you the standard deviation as well as the mean. And so you can record both of those numbers. So the standard deviation, if you include all the digits, and so we'll get into, the whole point of uncertainty analysis is so that you have some idea of, well, how many digits am I actually going to keep? So to start with, you'll just keep all of them. So 0.05019960159, etc. As long as you have pretty much all of them. And the mean, well, there weren't a terribly large amount of digits when we calculated the mean. The mean was just 1.68. So the mean here has units of seconds, and the standard deviation is also in units of seconds. So our mean was 1.68 seconds, and our standard, our deviation was around 0.05 seconds. And I'll highlight these as well. No, you'll never have to calculate standard deviation by hand. Maybe you have to do that in a stats class, but it's really not necessary here. I mean, sure, there's always value to it, but that's just not a great way to invest time as calculating standard deviations by hand. So yeah, so any calculation of standard deviations will pretty much always be done by a calculator. You won't have to worry about calculating statistical quantities by hand. All right, so the experimental value for time t, we've determined our average, our mean, and our standard deviation. And the standard deviation has a lot of extra digits, but the mean, it turns out the mean only has a few digits, but it's still if the mean had more than that, technically, the mean could have more digits. So I'll add extra zeros there because just in general, we've calculated, we're given extra digits with the standard deviation, and we could potentially have a whole bunch of extra digits with the mean too. So I'll add a couple extra zeros there to emphasize the fact that the mean as well as the standard deviation could have way more digits than you want to keep. And so we're kind of going through how we know how many digits we'll want to keep. So the number of digits that we will want to keep, it will turn out, will only be to the 100th place. Because if you go back to the simulator, you'll note that in the stopwatch itself, so our measuring device for the time, our seconds were only known to the 100th place. So that means that there's no way we could be more accurate than the 100th place because our measuring instrument itself was only accurate to the 100th place. So it would not be reasonable to keep an average period value that would be more precise beyond the 100th place because our measuring instrument, our measuring stopwatch is only precise to a certain digit, and that digit is the 100th place. And so, when reporting our experimental value for t, we have our basically our average period, which we've calculated, plus or minus our uncertainty. And so our average value is 1.68. And so we could, it's possible that when we did the calculation, if we would have had more digits of precision, we would have to truncate them to just two decimal places of precision because that's the limitation in the stopwatch. And so that's how we would truncate the mean. So the average period can't have more precision than the stopwatch itself, which is precise to the 100th place. Okay, but we still need plus or minus our uncertainty. And so plus or minus our uncertainty. And so, if we do use the standard deviation for our uncertainty, which is, is definitely not an unusual practice, we'll get into a little bit more at the end of the lab sort of unpacking, why is the standard deviation, the uncertainty that has to do with random error, but you can also have systemic error, which are, originate from a different fundamental place than the standard deviation. But if we use the standard deviation as our uncertainty, we would have 0.05 rounded to 0.05 again, because even though we have a whole bunch more extra digits with the standard deviation, we don't want the standard deviation. We want the decimal places to match. When we're adding or subtracting numbers, the decimal place has to match. And so the decimal place of our uncertainty has to match the decimal place of the value itself, which we determined was precise to the hundredths because of the stopwatch precision. So both those factors play in, that the average, the average value itself is limited by the precision to the stopwatch, and the number of digits that you report in your uncertainty has to match the precision decimal place, the precision of the decimal place in the average value there. So the decimal place of the uncertainty has to match the decimal place of the value. All right, then next is the theoretical calculation for the time. So our equation for the period of a pendulum, which was at the beginning of the lab, but we can repeat again here. The period is calculated as 2 pi times the square root of the quotient of the length divided by g, which will equal 2 times pi times square root of 0.7. So our known values, just entering our known values into the equation. So when show the calculation steps, this is what I mean by showing the calculation steps. Just do the equation and then plug in the values. So we have 0.70 meters for the length, for gravity 9.81 meters per second squared. And so when we crunch the numbers there, if we include all digits, we have 1.67, 8, 3, 9, 5, 8, etc. That's in units of seconds. All right, so the calculation steps would just be something like that, and then the calculation itself would yield, this number with a whole bunch of, with a large number of digits that's output by your calculator in units of seconds. So just like in the experimental value, the theoretical calculation for the period, even though when you calculate it, you can have a large number of decimal places, and theoretically you'd think you'd know all of these numbers, but you don't know all these numbers because when you calculated the period, the calculation originates from measurements of length and the measurements of the gravitational acceleration, which they themselves have limitations in their precisions. And so there's actually limitations in the precision for the calculation of the period based on the limitations of precision of what you've measured. And so moving from measurements, which have some uncertainty, and then you make calculations using those measurements, how do you determine the uncertainty in a calculation when it uses numbers from measurements, which they themselves have uncertainty. And so when you have that type of problem, at this level, the technique that we use is called the method of adding percent uncertainty. So percent uncertainty is just your uncertainty, except it's expressed as a percent. So it would be the ratio of your uncertainty divided by the number itself. So for example, in our experimental result, our percent uncertainty would be 0.05 divided by 1.68. And so that would give you a number that describes the uncertainty as a percent of the value itself. And so the method, we'll see how that method would be applied here. So basically, what the method says is that the percent uncertainty of t is the addition of the uncertainty of L and G. Since those are the two numbers in the calculation, it's possible to show that the uncertainty associated with L plus the percent uncertainty associated with G will correspond to the percent uncertainty of the period. So just as a reminder, I will repeat the equation for percent uncertainty. And so for t, for example, the percent uncertainty of the period t would be the uncertainty of t, which I symbolize with delta t for the uncertainty. The actual value is t. So just because we did talk about percent uncertainty in my lecture, but if you haven't seen in your lecture, the percent uncertainty, yeah, it'll just be the uncertainty, which would be 0.05 seconds divided by 1.68 seconds, of course, and that would be an example. So 0.05 divided by 1.68, so 0.02976, etc., which would equal 3%. So 3% uncertainty. So that's just an example. So that's not necessarily what you'd have to include in your answer. And so if you apply the method of adding percent uncertainty to this question, by applying the method of adding percent uncertainty, when you apply it to the calculated value of the period using an equation, we have two terms in the equation, a length uncertainty and a gravitational uncertainty. And so whatever terms you have in the equation, as long as those terms are multiplied or divided together, you can simply add them together. So you're adding percent uncertainty, and the two sources of uncertainty are your length and gravitational acceleration. So just when you apply the method, you're really just saying, okay, let's look at each term in the equation that has an uncertainty, which was length and gravitational acceleration. And if we add those two together, since those were the two variables present in the equation, the sum of those two will equal the percent uncertainty of the calculated value, which is the period. The percent uncertainty of the length is the uncertainty in the length divided by the length itself. Same with gravity. So the uncertainty of gravity divided by gravity itself. And plugging those numbers in for the length, we had an uncertainty of 1 centimeter, or if we convert that to meters, it'd be 0.01 meters. And the length itself, I'm using 0.7 meters, but you'll repeat this for 0.8 meters. And for gravity had an uncertainty of also had an uncertainty of 0.01 units of meters per second squared. And the actual value was 9.81. And so if you do all of those numbers, you'd have a large number of digits that you could potentially keep, but we'll just round to one significant figure, which would just be 1%. And so that'll be a pretty standard practice because there's only one significant figure in your uncertainties. So it'll usually work out to just have one significant figure in the final percent uncertainty. All right, so we have the percent uncertainty of t, of the period t. And we also have a calculated value. So the uncertainty of t can be determined by applying the equation for percent uncertainty again, except now we're applying it to the the equation rather than experimental data. So we've just calculated the percent uncertainty of the time as being 1%. We're looking for the uncertainty value itself, and the value of the period was calculated as 1.6783958, etc. So 1.6783 958 seconds. So we're still keeping all of the digits there. But if you solve for the uncertainty of the period, then will equal 1% times 1.6783958 seconds. Which again, so you'd have as many digits as you might think to keep. But since 1% only has, the value of 1 only has one significant figure, we'll just round this to one significant figure again, so 0.02 seconds. So again, we'll round to just one significant figure. Or, oh, actually, well, it's not, I guess we won't round yet. So all the digits would be 0.0678395 seconds. Yeah, so just repeating this number. Yeah, there could be more digits in there if we wanted. So all the digits, but we'll see how all of those, how when we round to one significant figure, how that'll play into the uncertainty. Yeah, so I've highlighted the main steps there that are, you know, satisfying the question. You know, if you know the unhighlighted parts are a little bit of background. So 0. Yeah, what I put. No, it's no. So well, it's 70 centimeters, which is 0.7 meters, and our uncertainty is 1 centimeter, or what would be 0.01 meters. Yeah, I've just included the, you know, significant figures on there as well. So all the digits for the uncertainty of t, you know, is to these two. But like I said, you know, if you you'll round the uncertainty to one significant figure because the 1% term has just one significant figure, and that originated from the fact that the uncertainty of the length and the uncertainty in gravity only have one significant figure. So it'll pretty much always work out to that, where the percent uncertainty will be one significant figure, and so the uncertainty as calculated, you know, using the equation would be one significant figure. So the uncertainty, you could say, you know, the method of percent uncertainty will almost always have just one significant figure. So because of that, you know, that's why we'll round the whole entire number of 0.0617, etc., down to just a single significant figure. So that would round to 0.02. So if the percent uncertainty is 0.02, you know, that will be, yeah, that'll be our uncertainty. So the theoretical result is plus or minus 0.02, you know, was determined using the method of adding percent uncertainty, and our calculated value, you know, came from above the theoretical calculation for t, 1.6783958, etc. All of those digits, those have to match the precision level of the uncertainty. So the precision of the value has to match the precision of the uncertainty. So the calculated value was t equals 1.6783958, and so if we match that decimal place, so specifically when I'm saying match the precision, specifically I'm saying matching the decimal place, which is the hundredths. Yes, this is going to be recorded, so if you want to watch it back, you'll have that ability. So so rounded to the hundredths place. You know, that whole long exact number 1.6783958 would be rounded to just 1.68 because rounding it to that hundredths place matches the hundredths place in the 0.02. So we have 1.68 plus or minus 0.2. All right, and so that, you know, is the two values that, you know, I'm really wanting you to get out of the lab. So we have 1.68 plus or minus 0.05 for the experimental result. So our experimental result, you know, is there's, you know, the result itself plus the corresponding uncertainty, and then so that's experiment, and then the theory 1.68 plus or minus 0.02. And so we do in fact find that they do compare. So we can even just compare them directly here. So our 6.8 plus or minus 0.5. Okay. Yeah. So they, you know, they match up pretty much, you know, right on top of each other, which is fine. So our theory and experimental, you can, yeah, I mean, it's, you know, they should be closely aligned. They won't necessarily be as exact as what I have here. Obviously, everyone will have their own unique data because you'll be starting and stopping the stopwatch yourself. And so you'll have your own unique data. So just by comparing those two, you can confirm that the theory is sufficient because you know, it appears as though the theory does in fact correctly describe the experiment. And so the errors associated here, or the uncertainties can always be categorized as one of two ways: either system error, which has to do with, you know, with the experiment itself. Was the experiment performed correctly? Was it performed as good as it can possibly be performed? You know, or was there some uncertainty that was, you know, associated with, you know, something just not precise enough, or perhaps, you know, the mass was completely measured incorrectly or something like that. So something associated with the experiment quality. The systemic error has to do with the quality of the experiment, and random error has to do with, you know, a more probabilistic uncertainty that can't be accounted for. So anytime you have random error or uncertainty associated with, you know, randomness with the experiment, that's type of uncertainty that you can't really predict or account for. It's totally random. So any type of uncertainty that you could possibly correct in some way would be system error. But any type of uncertainties that are just due to complete randomness that you can't predict or account for, that would be random error. So the length variable, we did measure the length as 70 centimeters plus or minus 1 centimeters. Would that be system uncertainty, or what would that type of uncertainty associated with the variable L be, you know, systemic, associated with the experiment, or just purely random? You know, I would call that you know, system error rather than random error, because that's the limitation of the measuring device. The length can't be measured any more precisely than 1 centimeter because that's the limitation of the measuring device itself. So it's limited by the experiment So there's something about the experiment that could be improved in order to get rid of that uncertainty. So limited by the experiment, the ruler only is precise to 1 centimeter. So it could be improved. The error with gravitational acceleration, that was also, an uncertainty associated with the system, the experiment itself. It's, we're, depending on where you are location-wise, the gravitational acceleration does vary based on your location, local geography, those sort of effects, are part of the experiment itself. It's not purely random because it's not like you're doing the experiment in a totally random location. You know where the location of the experiment is being performed. And so if you could have a better measurement of gravitational acceleration G, that would be, some way to improve the experiment. So it's a part of the system. So gravity is known to a certain precision, but it could depend on geographical location. So if you knew more about the local gravitational field, it could be more accurate. And then for the period variable, I think I put 2 rows in here, one for the experimentally determined time and the theoretically determined time. So I forgot to include the subscripts here. So one of these should be the period determined experimentally, and then another variable was determined theoretically from the equation. So experimentally, I would say this, you could definitely make an argument in the other way, but I think it's possible to classify that variable as random, with a certain degree of certainty. So the period, when we measured it, it was measured with the stopwatch. And so assuming that you stop and start as accurately as possible, you pretty much, there is the uncertainty associated with starting at the right time and ending at the right time is essentially random, because your ability to make it exact, you could argue is, sometimes you might stop the stopwatch a little late, sometimes you'll stop the stopwatch a little early, or sometimes you'll start it early or start it late. And so your ability to measure the period to a very precise level is limited by the fact, is limited by human reaction time. And so there's a randomness associated with our inability to be, more and more exact in when we start and stop the watch. And so it's random because we, when you're making the measurement by hand, you can't improve your reflexes beyond a certain point, and beyond that point, it's fair to assume that your ability to be consistent is essentially random. Yeah, so human reaction time allows us to be precise to a certain degree, uh, but if you're trying to start it and stop it very precisely, there are limitations to that, and I think it's fair to assume that um, sometimes you might start a little bit late, sometimes you'll start a little bit early. It'll be essentially random. But you could also argue that that would be a system error, because obviously if you use different technology, maybe some sort of light sensor to measure when the pendulum was at its highest point, then you can make a more accurate measurement. So in a sense, you can always argue that random errors are in fact system errors that you can just improve. Uh, but just conceptually, the difference between the system errors and random errors is a fallibility of the experiment versus just an intrinsic inability to predict what's going to happen exactly. If it's unpredictable, it's random. But if it's some imperfection in the experiment, that would qualify as system. So the theoretical prediction of the period t, would be, I mean, it's a calculation, but it's a calculation using two values that are systemic errors. So only um, because the theoretical is a calculation of using quantities that are associated with system uncertainties. Right. Yeah. So I mean, definitely try to express those ideas in your own words. Obviously, I tried to explain them, but translate those into your own words. Translate it in such a way so that you understand what I'm saying, but you're just saying it in your own words as best you can. And then finally, the last question is more of an in-depth uncertainty analysis, because it supposes, because obviously you're going to expect your data to agree, but it is possible in a real lab that you could have a theoretical prediction that's different from your experimental result. So this last question is sort of a hypothetical situation where you have an experimental result that doesn't match the theoretical prediction, even taking into account the uncertainties. So for example, in this hypothetical case, the theory and experiment don't match because the theory can be as high as 1.83, 1.83 seconds, because if you add 0.04, it can be as high as 1.83, but the experiment, with its uncertainty, the experiment can be as low as 1.87 seconds. So clearly, those numbers with these significant figures that we know to, those results don't match. And so how could you explain this discrepancy? Well, your first explanation, of course, is, well, you'll have two of them, but clearly either perhaps the theory is wrong. I mean, well, that would be explanation two. You should always assume that your experiment is wrong first, because it's easy to get the experiment wrong, whereas the theory has been around for hundreds of years. So your second explanation would be that the theory is incorrect or incomplete. Because if suppose if suppose like something was friction was an effect, because our theory is just that one single equation, allowing us to predict the period as a function of the length and gravitational acceleration, and there's no mention of friction. And so obviously, if you have a discrepancy, it could be that your theory is simply incomplete. You're not taking into account all of the possible effects that are actually present in the experiment. So that would assume that the experiment was done perfectly. So if you do an experiment simply perfectly, and you know that you did it perfectly, then that's really good data, because then you're so confident in your result that you can make a very precise measurement and actually critique the theory rather than critiquing the experiment itself. But that's more of the rare case. The first explanation is that there was some sort of system or random error that caused the discrepancy. And so what that means is, if it was the system, if there's a systemic error, so if there is some uncertainty or mistake introduced from something that's system, it's associated with the experiment itself. So perhaps the uncertainties were incorrect. So perhaps the uncertainty in the gravity or the uncertainty in the length are actually larger than what you thought they were. The uncertainty of the length of gravity should actually be larger than what they were. So it's an error in your ability to make measurements within the system. It could also be not just length of gravity. The measurement of time could be incorrect. So perhaps when you measure the time, maybe you have really slow reflexes. Your reflexes are so slow that you're off by 0.3 of a second every time. So maybe something like slow reflexes. So that's something that has to do with how the experiment was conducted itself. And then if it's random error, that means that everything was measured perfectly, and it was just by complete chance that that some fluke happened and you measured something extremely wrong. So if it's some random error, some sort of unusual event, or a rare fluke causing an extreme measurement. So when we're measuring the time, obviously maybe I did the experiment 5 times, but perhaps just by pure chance, each time I measured it just a little bit too short. Maybe I stopped it a little bit too soon. So maybe I was trying to preemptively stop the time measurement a little bit too soon, and I did that frequently enough to cause a repetition of bad measurements. So multiple bad measurements that happened randomly, essentially. And if it's random error, we did use the standard deviation, to calculate an uncertainty. And so if you do have random error, the standard deviation does provide you with certain levels of confidence of how confident you can be that it was random error or system error. So if you're so you might have you've heard the statistical intervals, 60, 68%, 95%, and then 99% for one standard deviation, 2 standard deviation, and 3 standard deviation. So basically, it could be a random error, but you should be able to evaluate sort of probabilistically how possible it could be due to random error. So, so if it's a random error, the experiment was still done perfectly. It just, by some, fluke, some rare event that's causing the measurements to be incorrect, the experiment was done perfectly, but yet we're still getting bad measurements. And so it could be random error, but you can sort of evaluate what's the chances that it actually was random error. And so that's when we use, standard deviation is useful for that, because you've heard of 1 sigma confidence interval, 2 sigma, and 3 sigma. And so if you're, if you record a data point that's 3 sigma away from the average, that means that you're really far away, and it's rare to get that type of measurement. That type of measurement would only happen 1% of the time, or 100 minus 99, or 5% for 2 sigma, or 42% for 1 sigma. So it is possible that some random effect happened, so that maybe there's some radiation that hit the inside of the stopwatch and caused it to read something different. Something really strange happen, but essentially random. So you can be, you have intervals over which you're confident. So like we said, the theory can be as high as 8.3, and the experiment can be as low as 1.87 within that 1 sigma uncertainty range. But we sort of identified 0.02 as the standard deviation, and so if we go to a confidence interval of 3 standard deviations, we would be at 0.06 and plus or minus 0.06, which actually would be within the theoretical prediction range. So, we could even write that down. So at 3 sigma, the experimental result would be 1.89 plus or minus 0.6. So just 3 times 0.02, 0.06, which could be as low as 1.83 seconds, which would agree with theory. So it is possible, if you had this data, you could conclude that, it could be a system error. So, so simply you made a mistake in the experiment. It could be a fallibility in the theory itself. But if it was random error, that would be, it would require a 3 sigma, effect. So basically, it would be very unlikely for it to be random error, because it would take, measurements that were different from the mean by a factor of 3 sigma, 3 times the standard deviation, which is, the first away, so it's the least likely to happen. That's so very unlikely, since only 1% of data will be 3 sigma away. So it's possible, but it is potentially possible. Statistically, it could be possible, but so you don't want to completely disregard it, but it's still very unlikely. Yeah. So basically, if it's a system error, basically it was a mistake in the experiment. So yeah, so really it's, you could expand explanation 1 into explanation 1 and 2. So in fact, you could have 3 explanations, where explanation 1 is a system error caused the discrepancy. Oh. It could also be, and then explanation 2, what it was random error caused the discrepancy. If it was a random error, I went through the explanation there. And explanation 3 is that the theory is incorrect or incomplete. So either friction wasn't taken into account, obviously air resistance could be a factor. Yeah, I think that's yeah, I'm just thinking. Oh, the string, or whatever is holding the pendulum, the string, or rod, whatever it is that's the body of the pendulum itself, whatever it is, the thing that's holding the mass, the string or the rod that's holding the pendulum mass, has an effect. So we didn't include either, the springiness of that string. So maybe the string or the rod, whatever is holding the pendulum mass and swinging it back and forth, maybe that has some effect on its dynamics, which it would, and that's not included by the theory. Well, yeah, it's it would depend on your data analysis. So right now, so for this hypothetical question, all we have is the results, where with these results, we would have 3 possible explanations why they don't agree. To actually pick one of these explanations, you would have to actually have the data and look at the data. And by looking at the data, you could have a better inference of which explanation was actually correct. So you'd just be able to, expound on each explanation. You really couldn't pick one explanation over the other, because you don't have any data, and so you wouldn't have any justification for choosing one explanation. So you'll just have to list them. But if you actually had data that had this discrepancy, then you could look at your data and see what is reasonable or what is not. If you did this experiment in the lab, I mean, yeah, it's obviously usually it's obviously either going to be the either an experimental error where you just made an incorrect measurement, or maybe you underestimated the uncertainty, because if you're very generous in your uncertainty, in the lab, you should always find agreement, because if you assume that you're not very precise, that gives you more wiggle room in terms of being able to match up experiment and theory, because your experiment will have a large interval of uncertainty, because if you're realistic, it would actually have that. But if you try to be really precise in your experiment, it's likely that the theory is incorrect or incomplete, because the mass of the string or the rod has an effect. It's, a string might stretch a little bit, so that's an additional way where, energy can exit the system from the swinging into sort of an oscillation of the springiness of the string. And of course, friction, obviously, does, almost always play some significant role as well. And so the theory in that sense would be incomplete. So yeah, depending on, your data analysis, depending on how precise you actually were in your physical experiment, you would probably choose, you would choose one of these explanations, depending on, did you think you did the experiment really precisely, and so it wouldn't be explanation 1, or perhaps, explanation 2, again, it wouldn't be random error, because if it is random error, then you should be able to, knock out explanation 2 by repeating the experiment. If you keep repeating the experiment, you should find that the random error goes away, because the random error is not repeatable, it's random. So yeah, so based on, if you actually did the experiment, you could choose which would be the most compelling, but to answer the question, yeah, you just make sure that you understand each one. All right, and then that's the lab. So yeah, that's, the highlighted portions are definitely the minimum of what you need. And so that's kind of like what I'm looking for in your submission. I think, having it formatted some like how I did it, I think that's, if you're comfortable with doing that, I mean, definitely go with that. As long as you have all the information on there, the format isn't extremely critical, but it should be, you want it to be easy for me to read so that you can get full credit. Yeah, so you'll be able to download this document off of Canvas. Yeah, I'll post it, briefly after this. Because after we have the Zoom, it does take some amount of time for the video file to get processed, so I can't do it right after, but it should be today, definitely no later than tomorrow, that I'll post the video, so that you can rewatch it if you'd like. But yeah, so that's the idea that today's lab is on. It's about yeah, it's using that link and using and filling in this sort of worksheet, so to speak. Yeah, I mean, any questions so far on what I've been doing? All right. Yeah. So I mean, we really don't have too much time left in class. I think I'll leave. So I think I'll leave the this Zoom meeting open until 1:10. If you want to, talk in the chat, or if you have a question for me, feel free to type something in the chat or turn on your webcam. But I'll keep the Zoom meeting open. If there's no questions, I'll just, mute myself and stop the video. But I will leave, but I'll still be here until 1:10. If there's any questions, then of course I'll leave the Zoom meeting open. So if you want to talk to communicate to other people, the class in the chat, feel free to do so. But I'll just leave it open so that you have available until 1:10 at least. So so feel free to work on that for our remaining time. But I'll also have office hours throughout the week if you have more questions, or you can just message me or email me. So we'll leave the meeting open for a little bit longer if there's any questions. But then I'll close out by 1:10.